Okay, so let's resume the course. So during the break, Abe-san found the reason why we got the bug in the previous lecture. Uh, so in the very latest version, we changed some material definition of carbon. And usually we used to assume that the carbon is a natural carbon, but now in the new version, we assume that the carbon is a combination of carbon 12 and carbon 13. But this change caused a bug. So in the previous input file, for example, bnct-4.imp, if you run fits with this definition, carbon definition, we get some very strange data, no dose. But if we add 12 here, so we got proper result. So we will check the reason of this bug more precisely and what condition make this bug. But anyway, please remember that carbon is better to be specified by carbon 12 instead of just C. But this bug doesn't influence the later part of this lecture. So if I run Bnct each dose, without specifying carbon 12, so as it is, we got rather normal data as we expect from the PPT file. So not always carbon need to be replaced with carbon 12, but still we don't know the reason, so maybe better to set carbon 12 in your input if you use version 3.33. So this is very specific to 3.33. The other versions are okay. Anyway, you got these results, I think. So boron dose, hydrogen dose, nitrogen dose, and photon dose. And the axis is fixed to 10 to the minus 17 to 10 to the 14. So you can directly compare it with these doses. And so I would like to explain how to calculate each dose component. So it is actually very complicated because in like a general tally function fits does not have the function to calculate the dose from each atoms. So it's quite rare that someone want to distinguish this dose come from hydrogen, this dose come from boron. It's only Bnct dosimetry requires that. Or maybe some other purpose that we need to do that, but it's quite rare. So its conventional function does not have, the conventional tally function does not have such function. So we have to use multiplier subsection, as Ogawa-san explained 2 days ago. And in the multiplier functions, there is a special way to consider the karma factor of a certain material. So if you specify two material number, for example, this case, material 2001 is hydrogen, and 1 space -4 indicates the neutron karma factor. So this is a special rule, and I don't explain the detail why this 1 and 4 here, but you can find it in the manual. So anyway, so we use the multiplier functions, and so to calculate each dose component, we use T-track instead of T-deposit. So dose is generally calculated by T-deposit, but in this case, we use T-track. And calculate the neutron fluence in the materials, and multiply with the karma factor of certain materials, such as hydrogen, nitrogen, boron. Then we can get each dose component. And to estimate the dose from each component, you have to input the density of hydrogens or nitrogen or boron to tally section. But the density is usually defined in material section, so you have to correlate the density to material sections and tally sections. And this is a way how to correlate the material section density to tally section density. So, and things are more complicated. So maybe it's so hard to follow my explanation. So maybe you need to look back, take a look back this page after finishing the course, I think. So you need to specify the atomic density in tally sections. But in the material section, you generally input the density in mass fraction. So there is a way to convert mass fraction to atomic fractions, and using these parameters, and convert the mass fraction to atomic fractions, and input the atomic fraction here. So actually, this is very difficult. I know that most of you are very confused right now, but this is a technique how to calculate each dose component. So basically, if you use this input file, you don't think about the technique behind that. So you can simply calculate each dose component using this sample input file. But if you want to know the detail behind that, please take a look back at these pages, and find out what we did behind this input file. Anyway, so let's change increase the boron 10 density from 10 ppm to 20 ppm, and see the difference. And here, C5 is a mass fraction of boron 10. So right now, 10 ppm, so 10 times 10 to the -6. So please change to 20 and run fits, and see the difference of boron dose here. Okay, so let's do this exercise. So when you finish this exercise, please press yes button. Okay, so I will do it on my screen. So change the density here from C5 here, 10 to 20, save, run fits. Then the volume dose is increased. This one is volume dose for 10 ppm, and this one is 20 ppm. So almost double, but the deeper location is slightly different, not double, because more neutrons are captured at the shallower locations. Okay, so next exercise is increase the neutron energy from 10 eV to 10 keV and see the difference of each doses. So I think it's rather simple exercise. Only you have to do is change the E0 parameter to 10 to the minus 2, 10 kb. Then you will get the different distribution. Basically, those are delivered to deeper locations. And particularly, hydrogen dose increase because hydrogen dose is come from rather high energy neutrons. So it's increased very much. The other dose, boron dose and nitrogen dose comes from the thermal, mostly comes from thermal neutrons. So they won't change that much. Only the relative shape is changed. But the hydrogen dose, quite big difference between the uh, uh, depends on the neutron energy very much. Okay, so next exercise is RV weighted dose using the Anatoly functions. So Anatoly is another something you never heard, I guess. It's quite advanced way of using fits. It can analyze the different tally result and merged into one output file. And the condition is that the shape tally date number of data written in each tally should be the same. For example, in this sample case, photon dose, hydrogen dose, nitrogen dose, and the boron dose can be added together with this ratio. This is a weighting factor. And the C90 is a normalization factor, those scaling factor. And here we simply set to 1. So what we want to do here is try to estimate the RV weighted dose directly from the FITS output. And for that purpose, we have to multiply 1 for photon dose, 2.5 for hydrogen dose, 2.5 for nitrogen dose, and 3.5 for boron dose. So you can set in this way and get the new result of named RV dose.out. And to run in the Anatoly function mode, you have to set ICNTL equal to 17. Then this Anatoly subsection start to work instead of conventional particle transport simulation. So with this mode, FITS does not transport any particle. Simply read the tally data and multiply this number and combine the data and output the weighted data to this file. And this N file indicates number of the data you need to combine. And if you set to 4, and you have to set the output file name. So this Anatoly read these 4 tally output and weight this weighted functions. And sum of the result given should be given in the RV dot out dose. And to use this function, you have to set IRESCHK parameter equal to 1. So otherwise, you may get error in the summing up stage. So the reason why we need this parameter is we in the unitary calculations. So fits check that every input should be the same or not. But these four data has slightly different format. So without this command, fits gives error that these four data are slightly different format. So to avoid that error, we have to introduce this parameter. Okay, so let's do this exercise. So change ICNT equal to 17 and comment out, delete the data before the iris check parameter and run fits and check rbdos.out and rbdos.eps file. Okay, let's do this exercise. Okay, so I will do it on my screen too. So exercise 8. So simply change the 17 and delete this one and run fits. So it suggests that you run fits with anatomy mode, and we got the RV dose. But RV weighted dose is so high compared to the previous dose because it is a sum of all those components. And in addition, RV or CV factor is weighted. So much higher than each dose component. So next one is the change of max value of y-axis of RB dose EPS from 10 to the minus 14 to 10 to the minus 13. So in the same as the other tallies, you can use angel command. So angel command is just change the EPS file. And if you add angel equal ymax bracket 10 to the minus 13, that means the graph, maximum value of the graph should be 10 to the minus 13 instead of 14. So you will see the data of RV weighted dose for shallower locations. And sorry, anatomy parameters should be defined between anatomy start and anatomy end. So in the anatomy section, there's some other parameters just before the anatomy start parameter. But this is this angel parameter should be within somewhere between these two lines. So the best position is here. So please add the angel parameter at these locations and run fits and see the difference. So I think you get this distribution. So the RB weighted dose is much higher than the each dose component. Okay, so I would like to summarize this lecture. For Bnct simulation using fits, use E mode equal to 2 when information of actual charge particle contributing to dose is necessary. But for classical Bnct dosimetry, you don't have to turn on the E mode equal to 2 because you need to calculate each dose component separately using the T-track section coupled with the multiplier subsections. And the RV weighted dose can be determined from each dose component with unitary functions. And this is completely another topic. It's related to the microdosimetry topic as I showed at the beginning. So conventional BNCT dosimetry, you can use a fixed RVE, but in reality, RVE is complicatedly depend on dose or dose rate, or sometimes like a intra and inter heterogeneity of boron-10 compound. And if you consider such detail in your RV estimation, you can estimate the photon isoeffective dose based on the stochastic microdosimetric kinetic model. And the example of this is given in this sample folder. So if you are interested in microdosimetric research in BNCT, please go to this page, this folder, and check the instruction inside that. Okay, so this is the end of my talk. And I'm sorry that we introduced a bug, so maybe you feel difficulty of BNCT dosimetry simulation. But actually, it's not so difficult if you use the sample input file given in this folder. So you can simply follow the method we propose to use. But of course, the technique behind is very complicated, so you must be you must take time to understand what is inside FITS. Okay, so I would like to finish the VLCT course and take questions. So if you have any questions, please let me know. Please turn on mic or write a message to chat. Okay, if not, yeah, so I would like to close this breakout room, and you can, if you go back to the main session, maybe accelerator shielding lecture is still going on, so you can take the last part of the lecture. So, yeah, that's all, and thank you very much for attending the BITS course and the BNCT course, and yeah, see you tomorrow.